Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing, lecture number 36, and here we will be actually studying what is known as an impact ionization and therefore its effect, what is known as a kink effect at higher values of VDS, right. Important why? Because again from the power perspective, if you do not consider this, you do not consider for the effectively a higher power dissipation which might happen because of an increased value of current in the low temperature region. So, we will understand what is the kink effect, we will try to see what is the impact ionization, then we will look into the factors which causes kink effect at cryo temperature, we will look at the onset of kink effect, and then we will relate the variation of maximum substrate current with temperature, and at when we apply a kink effect, what is the band diagram, and then finally the output characteristics of the device. Now, what is the kink effect? Let us first of all study that, and then we will take that into consideration in cryogenic temperature, right. Now, the kink effect is basically sudden increase, and that is let's not concentrate currently at nonlinear part of it, but surely it is a sudden increase, right. Let me change. There is a sudden increase, right, in the drain current of a MOSFET at very high drain to source voltages. So, what is plotted on the right hand side here is a drain current, right, in milliamperes with respect to drain to source voltage in volts, right. So, this is milliamperes and this is drain to source voltage for various values of gate voltages, right, which is at 1 volt, 2 volt, 3 volt, 4 volt and 5 volt. And then for each gate voltage we have varied the temperature right from 25 Kelvin to 12 Kelvin, right. And we try to see how does my drain current change with respect to drain to source voltage. So, one thing is absolutely clear that the qualitatively the variation of the current with respect to voltage is perfectly fine as per our knowledge, right. So, your drain current is on the y axis and since drain voltage is on the x axis. So, your conventional IDVD as we know for a bulk MOSFET is followed. Only thing is somewhere around this particular point, right, depending on the temperature, you see a sudden small change in the current which is basically nonlinear in nature, and then it becomes then it flattens out like this, right. And lower the temperature, the kink happens at a lower VDS. Higher the temperature, the kink happens at a higher VDS, and that is what is written in the second bullet, that creates a kink or a sharp bend in the drain to source voltage output characteristics curve. So, what is the origin of this one is primarily what is known as an impact ionization effect, right. So, this is impact ionization, and this generates why it is important impact ionization, because it generates extra carriers, right. How does it generate? As the name suggests, very high speed electrons will be traveling because your VDS is large, your electric fields are very large, they will be traveling with relatively a high drift velocity, strikes a particle, generates an electron and hole. Because of a strong electric field, these electrons gets accumulated and there is an extra current over and above the drain current which is actually flowing through the device, correct. This results in actually a reduction in the threshold voltage, right. And this happens because your bulk potential starts to increase and therefore your drain current tends to becomes larger, which you can see here for any current temperature here. We will discuss temperature part later on, but let us look at the fact that because of impact ionization, large current is there, your threshold voltage slightly reduces due to increase in bulk potential. And second thing is, as the temperature becomes smaller and smaller, the kink effect originates at a much lower VDS, and not only lower, but the absolute value of current also becomes larger at lower temperature, right. So, you see when you look at the 12 part, the 12 Kelvin part, right, let me rub this point. If you look at the 12 Kelvin part here, it is still the maximum which you get, right, and it becomes maximum here even for a fixed value of gate voltage. So, these observations you should keep in mind, right. So, lower temperature, the kink effect has a much larger role to play because the currents are much larger in this case. Now, let us look at the factor which affect the kink effect at cryogenic temperature. On the right hand side, if you look at the P substrate and N well, then typically we need not distinguish between the two at this stage, but typically what we are trying to look as that as the temperature goes to very low value, the relative resistance starts to become larger and larger, right. And the main reason why this happens is that you can explain it from these graphs and from these cartoons, that impact ionization at higher drain voltage causes a relatively larger bulk current. Why? Because you now have, if there is a potential in the bulk side, or even if it is grounded, there will be a charge carrier which will be flowing away from the channel onto the bulk, and that is what you see here, this part here. And therefore, it reduces the transistor's threshold voltage, and therefore your for the same amount of gate voltage your current increases, right, and that is the reason. Now the idea is that the bulk resistance actually increases by few orders of magnitude, right, and therefore there is an RB term coming into the bulk region. Why? Because this is the RB, which is the bulk resistance which falls down. So as the temperature goes on increasing, right, the effective impact ionization actually goes down, and therefore the bulk resistance goes down. That is shown on the right hand side. Look at the equivalent circuit diagram here. Then I have a gate terminal here, source and drain, but there is also a resistance term here which is defined as RB, and this is basically referred to as a bulk resistance, which is again a function of temperature and the bias. But since there is a current flowing through the p-type substrate, you will see that the resistance will be a function of the bias as well as on the temperature. Now, as I discussed with you, a noticeable kink appears in the output characteristics at higher voltages. It does not appear at lower voltages because the energy gained by the electrons at lower voltages is relatively very small to generate electron hole pairs, and therefore this phenomena happens beyond 4 to 5 volts, right, and then there might be a breakdown at a much higher voltage later on. Now, as I discussed with you, a noticeable kink is available to you in the output characteristics at higher drain voltages when VD is typically when T is less than 30 Kelvin, and that is the reason ID increases. Now, let us look at what is known as self polarization of the bulk. What is happening is that because of a large amount of impact ionization based currents which is flowing through the drain, there is also a current flowing through the base, and this is known as self biasing of the substrate. So, there will be electrons and hole pairs generated, and they will be always generated in pairs because you do not want to, or you can't have an electrical non-neutrality. There will be always an electrical neutrality, meaning that electron hole pairs will be always generated in pairs. So, if I say holes are generated, electrons are dragged by the drain side, but the holes are pushed into the substrate. So, there is a hole current which is moving to the p-type substrate, right, and therefore the resistance starts to fall down. That is what is written in the self polarization of bulk. Now what typically happens is, as you move across the cryogenic temperatures, the substrate resistance increases because the carrier freeze out. The impurities will actually freeze out drastically. So, the contribution of the number of particles, which is basically the holes in this case, will drop down. As a result, the back body bias temperature increases to a larger extent, right, and therefore the holes will be quickly evacuated to the body contact. Now, since the resistance changes, there is also a change in the bulk voltage, because your resistance has increased because of reduced carrier, therefore, which is the voltage drop will also be larger because of the increased resistances. That is what gives you much larger voltage drop across the bulk. And this voltage drop, as you know, the body effect, the threshold voltage reduces, and that further increase the ID. So, it's quite a complicated formulation. Reduce your temperature, and then at somewhere around 4 to 8 volts or 9 volts, you will see a kink effect coming because of impact ionization. Impact ionization generates electron hole pairs which are equally numbered because you do not want to compromise on the electrical neutrality. The electrons tends to move towards the drain side, the holes are pushed away from the gate into the bulk, and therefore there is a hole current available. But because of carrier freeze out, the value of the bulk resistance, which is RB, is large, therefore I into RB increases, the bulk potential increases, and that results in a reduction in the threshold voltage, which further increases the current. So, it is basically a dynamic process which plays out at very low temperature. Now, after the drain voltage, the kink effect actually tends to sort of merge out, which means that even if there is a kink, the overall current increases, but the total current still remains the same at larger gate voltages, and that is what you see here. As I say, they all tend to sort of bunch together at extremely large values of VD. Now the temperature dependence, as I told to you, that the kink effect is more prominent at lower temperatures and higher gate to source voltage, obviously at higher drain voltage as well. Now the excess current is modeled as this, right, ID equals to GB. If you remember, GM transconductance, this is body conductance, GM is del IDS del VDS, right, and GB is bulk to substrate, you can write it is del IDS del VBS, it bulks to source. So you say that your drain current is not only a function of the gate voltage but also a function of the substrate bias, and that is given by del ID equals to GB times VB, right, and VB is the applied bias at the back end side which you see. Now let us look at the variation of the substrate current with temperature for N and P type device. So on the right hand side, if you see, we have plotted the maximum substrate current with respect to temperature, and interestingly at cryogenic temperatures, which is somewhere here, the PMOS substrate leakage current tends to become larger as compared to NMOS, whereas as you go to higher temperature, NMOS is obviously larger as compared to PMOS. Understanding it higher is relatively easy. Why? Because at higher temperature NMOS has got lower effective mass, and that is the reason the current becomes larger, leakage current. Now let us come back to the kink effect and its implication on the PMOS circuitry. Now we know that the substrate plays a major role in varying the threshold voltage of the device. We also know that impact ionization near the drain end also plays a major role in the kink effect and the hot carrier degradation. We will not go into the hot carrier degradation now, concentrate on the kink effect in a sense. Now the reliability of the MOS device, right, at cryogenic temperature also becomes a function indirectly as a substrate current at the cryogenic temperature. Ideally I do not want any substrate current to flow because I do not want any bulk potential to happen, but because of impact ionization is relatively lower temperature and at relatively higher VD, there will be a substrate current, and that is what is written here, that there is a substrate current at cryogenic temperatures, right. If you look at the substrate current, there are many models for the substrate current. Let us not deep dive into at this stage, it is too early, but we will surely know that most of the classical substrate model is valid up to 4 Kelvin, right, which is liquid helium temperature. Below that, at even below 4 Kelvin, somewhere around millikelvin, there is a carrier freeze out drastically happening. But two things to take away from this slide is, at lower temperature, PMOS contribution in the substrate current is much larger as compared to NMOS. Again, the same thing which we are saying, that NMOS exhibits a much higher substrate current than PMOS when somewhere at the edge, when you have 300 Kelvin, right. Now this is again, as I discussed with you, higher electron mobility and higher impact ionization for electron as compared to holes. You should understand one important point, that once the electrons and holes are generated by impact ionization, right, these tend to separate out because of the electric field, but electrons being relatively lower mass, effective mass, they separate out earlier as compared to holes. So the holes sort of, in a sense, sort of lags behind the formulation. It lags behind in terms of formulation. Now if you look at this part here, then you will look at the fact that the temperature dependent substrate current is always available with you, and it varies from 0 to 300 Kelvin. However, NMOS post cryo is relatively steeper as compared to PMOS. If you look very closely here, NMOS dropping down its substrate current at which temperature is much faster as compared to PMOS. Now there are two ways of modeling the current, and that can be shown here in this graph. It depends upon therefore the drain voltage. It also depends upon the value of your VDS sat, which is the saturation drain to source voltage. More is the difference between VD and VDS sat, lesser will be your impact ionization, which means that if your applied VDS is very close to VDS sat, saturation drain current, your impact ionization profile will be relatively smaller, right, and that is one of the reasons your substrate current will be relatively smaller. But if your VD is much larger as compared to them, you will get a large impact ionization available to you. Let us come to the substrate current modeling now, and it is given as IB equals to A times ID exponential minus B by VD minus VD sat, right. Now let us look one by one. If Vd equals to Vd sat, then the denominator becomes equals to 0, right, and this becomes exponentially negative infinity, which means that IV will be almost going to 0, and that is true also, right. So when you have your Vd and Vd sat very close to each other, you will have this problem of lowering of the substrate current. And then A and B are basically constants which depend upon the ionization length, which is L, right. Now if you look at the ratio of base current to the drain current, and if you plot that with respect to 1 by Vd sat, then you will see a linear relationship which is happening right from wide range of temperature 20 to 300 Kelvin. The variation will be almost linear, which effectively means that the ratio of substrate current to the drain current, because of, and substrate current as you have seen is directly dependent upon the impact ionization part, becomes direct dependency on Vd minus Vds sat. Now let us look at the band diagram aspect of it, right, and let us see how the band diagram works in this case. The horizontal axis is of course the energy scale, and this is the distance scale which you see potential, and as you can see, because of impact ionization on the drain side, the energy band actually skips forward to a higher value, right, skips forward to a higher value. So this is source on the left hand side and this is drain, right, and this results in a large EHP electron hole pair generation which takes place. Lower potential therefore suggests a high energy for electron because there is a negative sign attached to it. Now let us look at the normal potential profile. If you look at the ideal operation, there will be a smooth change in the source to drain, and the electrons will therefore accelerate from drain towards the source end by applying a positive drain bias. However, there will be a distortion because of kink effect near the drain edge, right. The potential will suddenly distort. You see this dotted curve, if you see sudden rise is there or a bump is there there is a bump up in the kink region, right, and that sudden distortion in the potential takes place, and this is caused primarily by impact ionization. And if you look very carefully, that does not happen near the source end to a larger extent. It primarily happens near the drain end because the electric fields are relatively larger. Moreover, because of high electric field at the drain end, the electron hole pairs are generated, and these electrons are collected by the drain and the hole gets trapped by the body. The body has got a bias attached to it. This is the band diagram which I wanted to show. Similarly, the trapped holes will therefore raise the local body potential, which we have already discussed, and when this changes, the effective potential seen by the band is slightly changed, right, and therefore locally the band structure moves upwards, because you see when you apply a gate bias it will move down because you are giving Q into Vd, but because of the positive charge it is in the opposite direction, this starts to move up. So it is not as down as you expect, it starts to move up because of the body potential, and this reduces the threshold voltage, causing a spike in the drain current, right, and we have already seen this point. Similarly, there will be also a forward biasing of the source body junction. We have not still talked about source body. Source body, you will also have a depletion region, right, and as the body potential tends to increase, source is grounded, please understand, the source body PN junction starts to behave like a forward biased PN junction, because substrate is P type and your source is N type, and you are giving a positive bias on the substrate side, and therefore there will be a forward biased PN junction, and this allows you to have a larger additional current from source to the body and then to the drain. Now let us look at what are the consequences of distorted body potential. The consequences are that the sudden increase in the current looks good, but from a power perspective not a good idea. Further, because of this kink effect, sudden rise in the current because of temperature, the device reliability and a large noise gets inserted, right, and therefore signal to noise ratio tends to fall down in such a scenario. Why? Because the current increases, not only current increases, the noise also increases drastically because of the kink effect, and that is the consequences of the band profile, a distorted band profile between source and drain due to impact ionization. We have already discussed this. Quickly we will go ahead and do the quick recap of the equations which we do for kink effect. This is GB into VB. So if you want to predict the drain current because of the impact ionization, please predict the value of the body transconductance, multiply that with the body potential, and you will get whatever delta ID you will get. Similarly, the relationship between GB and GM can be written in this manner, that GB equals to CD by Cox into GM, where CD is basically the depletion capacitance and Cox is the oxide capacitance and GM is the gate conductance. We need not go into details of how this is formed, but which effectively means that GB by GM is a function of CD by Cox, right. So, if you lower your oxide thickness, your Cox increases, right, and therefore by GB my GM reduces, which can only happen if my GM increases, right, and that is true also. If you reduce your dimension of the oxide thickness, gate has a better control and therefore the GM becomes higher and GB by GM actually falls down. The change in the threshold voltage, just note down the equation at this stage, is delta VT equals to minus CD by Cox into VB, where VB is the potential. And therefore, and this is quite interesting, and therefore because of impact ionization, this equation expression CD by Cox is quite critical. That means the ratio of the depletion capacitance to the oxide capacitance becomes quite critical, and this results in the decrease in the threshold. So, higher the ratio of CD to Cox, more will be the change in the threshold voltage. What is CD? CD is the depletion sort of capacitance. That happens because there is a depletion layer formed just below the inversion in this case. And that is the reason you have a change in the threshold voltage, which is a direct function of the depletion width. Now, let us look at the IDVD we finalize at around 900 Kelvin. These are all measured sort of results which we get, and the drain current if you plot with respect to gate voltage for various. And one interesting point which I need to point out, which I leave as an exercise to you again, is that typically if you work at 300 Kelvin at very high drain voltages, you actually see shootout. So, it is something like this, it becomes very large. So, breakdown happens at 300 Kelvin, 300 Kelvin. However, at 9 Kelvin, the current actually starts to dip at very large values of drain voltages. So, if you look at the 6 volt VG and you try to find out the drain current with respect to drain current with the drain voltage, you see there is a drop here actually. Similarly, if you look at the other characteristics, there is a big drop. Just try to find out. This is for a SOI MOSFET, silicon on insulator MOSFET. Now, as I discussed with you, at lower values of VG, you can see there is a small amount of kink effect happening at these two places. And the kink effect, as I discussed with you, is more pronounced at low voltages and less at the high voltages. And this is primarily, at this stage we will not go into details, but primarily because of self-heating limiting impact ionization, right. So, impact ionization has an effect on self-heating which reduces the kink effect. So, therefore, finalizing our whole idea, in accumulation mode there is no kink effect. If you do an accumulation mode device characteristics, it gives you a better suitable characteristics for cryogenic operations. Moreover, for most of the cryogenic operations, absence of kink effect in accumulation region is a good idea when you do a cryogenic analog mixed signal design. Enhancement mode devices shows you a much better temperature controlled or temperature dependent behavior, and that is the problem which typically one faces at cryogenic temperatures, right. So, with this, let me recapitulate what we did for the previous half an hour. We looked into what is known as the kink effect. We also looked, and the reason for this was impact ionization, and how we look into the physical meaning of impact ionization, what is the physics behind the impact ionization, where it gets influenced, how does impact ionization is a function of temperature when you plot ID versus VDS. And then we looked into various types of devices and we saw that there are various substrate models available, substrate models. Then we looked into that change in the substrate bias is there because of impact ionization, which also influences your threshold voltage to a larger extent, and threshold voltage change is a direct dependency on the depletion and the oxide capacitance totally. We finally looked up into accumulation mode and inversion mode IV characteristics, and finally ended up looking at the one of the major sort of, not a major but one of the good sort of, I should say, replacement for bulk MOSFET is a SOI devices, silicon on insulator devices, because of reduced kink effect and reduced variability in a sense. I hope you enjoyed this lecture. We will meet next time. Thank you.